Hello and welcome back to another video with It's Dr. Dan, and today we're going to be learning how to balance redox reactions, specifically those in acidic solutions or acidic mediums. So the way that these different problems generally always look is that you'll be given a problem that's going to have all these imbalanced charges on it, and it's going to specifically tell you, hey, you need to balance this in acidic solution using the half reaction method. Now, when we kind of see these are all about oxidation and reduction, and they can be a very confusing problem that can involve many steps to how to do them. But the thing is, it's very systematic and very procedural, meaning it's going to follow very specific steps when we are going to go through these. So, looking through these problems, it's all about that oxidation reduction, meaning it's all about the gaining and losing of electrons. So just remember Leo goes grr, and you'll remember how to do these different problems and how to label them. So in this video, we're going to go through specific steps, and we're going to show you exactly how to do this kind of problem. Let's take a look. The problem that we're going to be working on today is going to be the following one. So generally the way that these problems are written is it says complete and balance the following equation in an acidic solution using the half reaction method. Now, keep in mind, acidic solution could be worded some different ways. You could see it say acidic medium, it's the same idea, or it could say the word acidic over the yield arrow of the reaction. So when we're kind of looking at this, you can't just balance it just doing your coefficients. Generally, whenever it is specifically stated to do the half reaction method, you got to go through different steps. The only time you can ever try to balance it is if all the charges end up balanced. So this is a very specific method, adding waters and hydrogens and different types of contexts like that. So we're also going to practice labeling the oxidizing and reducing agent as well, being that a lot of these problems ask you to label everything on top of it. So this tends to be the challenge problem of a lot of exams in General Chemistry 1 and 2. So we definitely want to make sure that we're able to follow these different steps. So let's get into doing this problem. Okay, so this is all the specific steps to doing this problem. And as you can see, it is a long list that can look very, very overwhelming, but I thought I'd put it here just so that we have the entire process of how to do this. The first thing we're going to do is we're going to determine the oxidation numbers. Then we'll write the half reactions. Then we will balance all atoms that are not hydrogen and oxygen. Then we will balance the oxygens by adding water, then the hydrogens by adding H+, then we'll balance the charges with electrons, and then we will then go through the half reactions, combining them and canceling anything that is similar. So we're going to go through this step by step on the problem that I showed above. Let's get into our first step, identifying the oxidation numbers. Okay, so the first step, determining oxidation numbers. This is a set of different rules that do exist for trying to identifying these imaginary charges that we have on these species. So the first thing is just kind of reading through them, right? If an element's by itself, it's 0. If you have group 1 or 2, it follows their charges, right? Halogens are generally -1, unless if they're bound to oxygen, then they can be positive. Monatomic ions always equal their ionic charges. Hydrogen is always assumed to be +1 when it's bound to a nonmetal, -1 if it's bound to a metal, and then oxygen is always -2 unless it's in a peroxide, and then fluorine is always -1. Now, the biggest thing is that the sum of all the oxidation states has to equal the charge of the compound, meaning that if you have something that's neutral, it must be overall equal to 0. And then if you have an actual ionic compound, then it has to equal the ionic charge. So if we were to try to go through this, identifying all of our states. Now, the reason why we do this is so that way we can figure out what's being oxidized, what is being reduced within the given problem. So if I look at the first one, right, I have iodine 2. That is the natural state of that particular compound, right? The diatomic 7, the 7 diatomics, I2 is one of them. Then what we go to is our next one. We have OCl minus. So overall, it has a negative charge. So what we got to go through is thinking of all of our different rules that we have above, right? The first one is that oxygen is usually -2. So what that means is chlorine must be +1 in order to make the overall negative. Then we're going to go to the next one. So the way that one way I like to do these is I like to make like a little chart under each of these species. So that way I can help assign oxidation states. So if we kind of think, right, oxygen is -2. So that means overall we have an entire -6 for all three oxygens that are there. So this helps us do the math in our head for what's iodine, right? So in this case, iodine must be +5 in order to make the entire thing equal to the -1 that's there for the charge. And then chlorine is already -1. All right, so now what we are going to be doing here is we can now try to label which elements are getting oxidized, what's getting reduced. So we're looking for anything that's changing values. So when we kind of look, right, we can see the iodines, right? It goes from 0 to +5, meaning it's becoming more positive. So that means it is losing electrons. So that is being oxidized. So specifically, iodine is being oxidized. Now, when we go to the next one, we're looking for another species, and we can see the chlorines, right, are going from positive to negative. So we'll label those ones as well, right? So positive to negative, being more negative means that chlorine is being reduced. So our other question was all about, oh, can we label what's actually our oxidizing and reducing agents? And we could do that now. So keep in mind, it's kind of like trying to identify the chaos agent in these cases. So whenever we say chaos agent, that means they're causing chaos. So when we label oxidizing agent, it's what's causing oxidation. Same thing with the reducing agent. It's what's causing reduction, meaning they're a pair. So in this case, if I have iodine, iodine I2 is being oxidized. However, it's causing the reduction. So that makes it the reducing agent. It's like the opposite when we're looking at each of these pairs. So in that case, being that chlorine is being reduced, so that means that OCl in this case is the oxidizing agent. Okay. So that is how we would label them, being it's all about what they are causing in a given reaction. All right, let's take a look at our next part where we're going to write our half reactions. All right, so now we're going to be writing our two half reactions, which is based on what's being oxidized and reduced. So first we'll write down that we'll have our I2, right? So being that this one is being oxidized, we're going to match it with its partner. So we have IO3 aqueous, and that's going to be one of our half reactions. Then we'll do the same thing for OCl minus aqueous, and we can write that that's going to go to chlorine. Now, for this part, you could potentially ignore labeling things that are oxidized and reduced because it's all about like which ones are matching the best. But it's always safe to try to label everything to make sure you do match it correctly, especially if you're relatively new to oxidation reduction. Generally, these problems always ask you to label everything, so you should write down each of the different pairs. Okay, so we have our oxidized, and then we have our reduced pair. Now, what we're going to be doing for the next step is we're going to be balancing everything, all atoms that are not hydrogen or oxygen. So what you need to now do is you got to look at your two half reactions and see, is there anything that we can, that's not hydrogen or oxygen, that's imbalanced. So if you look at the top one, we can see that the iodines, right, they are currently not balanced, right? We have I2 on the left. So we're just going to treat it like a normal problem, like a normal balancing problem. And we're going to put a coefficient of 2 in front of it to balance our iodines. Now, keep in mind, the O's are not balanced, and you can maybe even notice that there's no oxygens on the left. So that's where the acid balancing comes into play. Now, if you look at the bottom, right, you can see your chlorines are good, oxygens are not. So this is where it's going to go into our next step, where we're going to balance things in the following order. We're always going to do what I refer to as other atoms, right? So that was like our iodines. Then we're going to do oxygen, then hydrogen, then the electrons. So let's go to our next step. And what we're going to do is we're going to do this just for one of the halves for now, and then we'll do the other one in that entire order in one straight shot. So let's start with the iodine and go through our steps. Okay, so our fourth step, we're going to be balancing the other elements. So we're going to start with oxygen, then hydrogen. So the way that we balance our oxygen is we're going to be adding water to the mix, meaning that for every oxygen that you have present, we have to add a water in order to balance it. So like on the right-hand side, right, I have a total of 6 oxygens that are there because I have 2 IO3s. So what does that mean is that I have to add 6 waters to the left-hand side in order to balance it. Now, why water? Why am I doing that? Well, it's all about the problem, right? So notice how it says acidic solution. So what does that mean is solution, solvent, solute. So the solvent is water, right? So this is something that's occurring in water, and there's going to be acid involved, meaning that there's going to be protons that are going to be floating around. So not only do I add water, but I also have to balance those hydrogens I just added by adding protons. So being that I added 6 waters, that means you added 6 hydrogens. So I'm going to balance that by adding 12 hydrogens to the other side in order to balance this. Okay, now this brings us to our next step, is when we add electrons to balance the charge. So what does that mean? Well, the whole idea of oxidation reduction, in order to have a balanced oxidation reduction, is that charges need to be balanced on the reactants and product side. So if I kind of like look at all these species that are on the left, right, all these are neutral. So what you can see is everything on the left, it has a total of a 0 charge. But if I kind of look at the right-hand side, I have positive ions, I have negative ions. This is something where if I add up all the charge, right, I have a total of 12 plus just from the hydrogens alone, and then 2 negative from the iodates. So what that means is I have a total of 10 plus on the right-hand side. That is clearly not balanced. So what we are going to do is we're going to add electrons in order to balance the charge. So I added 10 electrons, and what that's going to do is that's going to then cancel that to also be 0. Because remember, it's all about electrons being transferred from one side to the other when we're kind of doing these problems. So now what we're going to be doing for the next part is we're going to be doing this for the other half reaction as well. So we completed our iodate. That's all of our steps for that part. Let's do the same thing for the other. So we didn't forget about the other half reaction. I just wanted to show you with one half first, just so we don't have a million things on the page at one time, because these are big problems. So we're going to now do the exact same thing, but a little bit quicker, right? So remember the order: other atoms first, then oxygen, hydrogen, electrons. So just in that order. So other, O, H, E. Kind of remember that. All right, so chlorines are our other atom. They're balanced. We're already done that step. Next one is we're going to balance our oxygens by adding water. So on the left-hand side, I have 1 oxygen. So what do I got to do? I got to add 1 water to the left. Now, being that I added that water, I got to also now balance my protons. So I'm going to add 2 protons to the left-hand side. And now what we're going to do is we're going to check our electrons, right? Which was our overall charge. So I can see on the right-hand side, I have -1 because I have that 1 chlorine. And then on the left, I have 2 protons, so 2 plus, and then a negative. So that means I have a total of +1. All right, so that what does that mean is how do I get them to be equal? Being I need to add my electrons. So the only way to do that is if I add 2 electrons to the left-hand side. That will now make this entire left side -1 as well. So this will be our half reaction for the reduction side of the problem. Now let's put it all together. Our next part is all about canceling the electrons, right? You've never seen a chemical reaction where the electrons are listed in the reaction, so we have to cancel them. Now, the only way that's possible is when we multiply these half reactions by some kind of factor to get the electrons to be equal in the top and the bottom. So first thing is, before you kind of go anywhere, is always double check your work. Make sure that there's electrons on the left and the right hand side of the equation. If they're on the same side, that means you did something wrong when it came to calculating your charge. Same thing with hydrogens. Generally, they're on the opposite side as well. So double check that too. So in this case, like you see that we have 12 on the right on the top one and then 2 on the left. So what we need to do is we need to make them equal. So being that the bottom is a smaller number, what we're going to do is we're going to multiply the bottom by 5. So therefore be 5 times 2 electrons. So what we're going to do is we're going to rewrite the bottom timesing everything by 5. So I have 10 electrons, I'll have 10 protons, then I'm going to have 5 OCl minus, right? And I'm going to have 5 chlorines, and then we will also have 5 waters that we're going to have on the problem. Okay, so we multiplied everything by 5. Now, so what that means is we can kind of get rid of this entire thing on the top. We don't need it anymore. So we'll get rid of that. All right, so now what we'll do is we can now put the two equations next to each other. And this is where our next step is going to come into play. Okay, so our last step, what we're going to be doing is we're going to be adding things together almost like a math problem. So we're going to add together the two half reactions, and then we're going to cancel anything out that's matching on the left and right hand side. So, like for example, the electrons will get canceled, right? So we have 10 electrons on the right, 10 on the left. So something like that is going to end up getting canceled. Now, what else is going to get canceled is anything else that matches. So notice how we added waters and hydrogens to the mix. Those are things that we're looking for. So we had 5 waters on the right. We had 6 on the left-hand side. So what does that mean is that we're going to end up reducing that coefficient down to 1, right? Put 5 into 6, we'll have 1 left over. Same thing with the hydrogens, right? So I'm going to cancel all of the ones that are on the left-hand side. And as a result, we're only going to have 2 hydrogens that are going to be remaining on the right. So now what we're going to do is we're going to take everything and add it together into one big reaction. And that's going to be our final answer. Is going to be our balanced reaction. So, right, we have 1 water. And this is the kind of the part to be careful with. Make sure you're getting everything. It's so easy to actually miss something, right? We have our iodine. Then we have our 5OCl minus, and that's all going to be everything that's on the left. Now we have our 2 iodates, IO3 minus, and that's aqueous, and that's going to be added to our 5 chlorines. And then the only thing left is our 2 hydrogens, right? So I'll put them back in their green, and that shows that we have our acidic component in the reaction as well. And those are going to be aqueous as well. So that is our entire balance process. It was very long, right? It's a lot of steps. So let's take a look and just summarize all what we just did. All right, that's our video, right? So this is all those different steps that we had to go through. And you could see that it was a lot, right? Especially when we started with the following unbalanced equation and we balanced it. So one of the things that I would really recommend is kind of just, it's really boils down to just a few steps. Is first you write your half reactions, then balance it other atoms first, then oxygen with water, then hydrogen with protons, and then balance your charge electrons, and then combine them. It's very procedural. It takes practice with anything, but you can do this. If you can conquer this, arguably, this is probably one of the hardest things you have to achieve in general chemistry 1 or 2 that does not involve a lot of math. So, especially in terms of balancing, this is probably the most difficult balancing process. But if you can do these, you can really handle any type of balancing. Okay. Well, thank you so much for listening. And if this is your first time here, please hit that like button, subscribe to the channel to keep helping it grow, help reach more students just like you. And thank you so much for being here. I really appreciate it. And if you have any questions, please put them in the comments section below or send me a message if you're one of my students. All right. Thank you so much. And I'll see you all later. Bye now.